Hello students, welcome to lecture 32 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on miniaturized design of microwave antennas. So, here is the lecture outline. We will discuss different design models of microwave antennas and then we will go into a miniaturized design of the antennas. So, in the earlier lecture, we saw the results of FDTD simulations of the S11 spectrum, that is the reflection spectrum. Okay. So, today we will start with the far field patterns. So, the far field patterns evaluated in H and E planes for all the antenna models that we discussed earlier. Okay. These are these 4 models are basically shown at their own resonant frequencies, right. So, this figure 1 tells you about the H plane characteristics, and this is the far field pattern in E plane. Okay. So, here different types of lines basically tells you the 4 models. So, A is basically telling about the standard inhomogeneous analytical model, B is standard homogeneous numerical model, C, that is basically this dotted lines tells you standard inhomogeneous numerical model, and finally you have D, which is a miniaturized inhomogeneous numerical model, right. So, remember they are all calculated at their respective resonant frequencies, right. So, as you can see from the figure that no significant differences are observed between the analytical and numerical field patterns except for the back lobes. Okay. So, the back lobes are in fact mostly absent in the far field patterns of the analytical model, and this is due to the consideration of the antenna model as infinite in the direction of z axis. The analytical modeling using the equations and the numerical modeling using the FDTD commercial software have shown 2 important things. First, that the maximum power gain of standard homogeneous numerical model is around 4.6 dB, and it was found at -2 degrees, that is theta equals -2 degree. Also, it is found that the appropriate efficiency value comes out to be around 40.72% in the case of standard homogeneized numerical model, right. Now, in the case of standard inhomogeneous numerical model, the gain, so that is case B, okay, the gain was reported to be around 4.84 dB, and it was found at theta equals 0 degree. Okay. The efficiency value came out to be 42.76% in this particular case. In the standard inhomogeneous numerical mode, the gain was reported to be maximum, okay, and there you got around 5.01 dB at an angle of theta equals -2 degrees with an efficiency of 43.98%, right. So, these results are basically in good agreement with the main idea of the study, which basically focuses on improving the antenna's performance using composite or metamaterial structures. So, in this study, FDTD simulations for near field around the antenna is performed in 2 mutually perpendicular directions. Okay. So, the corresponding fields are basically plotted in this figure 1 and 2. So, here you can see in figure 1 you are plotting the near field calculated at the cross section in basically y equals 0 plane of the patch antenna. Again, A stand for the standard homogeneous numerical model that has a resonance at 7.307 gigahertz. Okay. Then B for standard inhomogeneous numerical model having a gain at 7.383 gigahertz, and the last one is for the miniaturized inhomogeneous numerical model having a gain at 7.326 gigahertz, right. So, this is for the near field calculated of the patch antenna at y equals 0 plane. Now, in figure 2, it basically shows you the near field calculated in the middle cross section along the x axis of the patch antenna again for the 3 cases. Okay. So, these are all V by M. So, these are basically electric field values which are plotted. Now, as you can observe in these figures, the implementation of the composite or metamaterial substrates basically result in considerable decrease in the intensity of the near field around the antennas, as you can see here clearly, right. So, this result is specifically important with a viewpoint of creating gadgets, because of the possibility of a considerable decrease in the negative impact of the EM radiation, on humans and other living objects. Okay. Moreover, as was also shown by Rybin's group, such antenna can be basically used for creating novel transponders, okay. Thus taking into account the above performance analysis of all this kind of considered antenna models, we can say that the proposed analytical model of the rectangular patch antenna can be used for designing patch antennas of new generation. So, let us find a miniaturized design of a microwave antenna for the given values of d, epsilon r, mu r and resonance frequency f r. So, taking into account numerous FDTD simulations, we are able to obtain the appropriate antenna design with length of 0.0117 meter and width of 0.156 meter, okay, resonating at 7.418 gigahertz, right. So, throughout the study we will basically call the approximate antenna design of, will call the approximate or appropriate antenna design the miniaturized inhomogeneous numerical model or design, right, and this was evaluated at 7.418 gigahertz, as you can see. Now, it is important to mention that the miniaturized design theoretically gives the most impedance matched antenna, okay, compared to all previously considered antenna designs in the study, and now moreover no significant differences are observed between the far field radiation patterns of the miniaturized antenna design, okay, and the other antennas presented in our resonant frequencies, except for the back lobes, as you can see in the figure. So, the intensity of the near field around the miniaturized patch antenna is less than that of the standard patch antenna on the dielectric substrate, right. So, in order to evaluate the advantage of the miniaturized design in the volume profile with regard to the analytical design, let us use this volume profile miniaturization gain factor. It is also called VPMGF, okay, and you can obtain this as 1 minus W mean times L mean divided by W into L into 100%. So, here L mean and W mean are basically the length and width of the patch in the miniaturized design. So, this gain factor basically indicates the reduction in the antenna size due to miniaturization. So, in fact, VPMGF can reach larger values for large real part of the effective relative permittivity of the composite and or we will say metamaterial substrates. So, the last miniaturized design has shown that the miniaturization of rectangular patch antenna on enhanced non-resonant composite metamaterial, which has got real part of the relative permittivity positive, also the permeability is also greater than equal to 1, that is possible in principle, right. Moreover, its quantitative estimation can be evaluated using this formula, okay. So, that tells us the effect of this volume miniaturization. However, you will see that the equation says nothing about how to calculate this values of L mean and W mean directly. So, in other words, the appropriate miniaturization concept for rectangular patch antennas is required, and the concept will be able to bring breakthroughs in the domain of compact antennas with extra capabilities of reconfigurable and wearable antenna systems with regard to band tuning operation, beam steering operation, and so on. So, we found that the volume profile of the rectangular patch antenna on substrate created on the basis of enhanced non-resonant composite or metamaterial is being decreased by increasing the value of the real part of the complex effective permittivity of the substrate. Now, in this way it is logical to answer the question like to what extent can we increase the value of the real part of the complex relative complex effective relative permittivity of the substrate in order to minimize the antenna's volume profile, right. So, in order to answer that question, we have to solve the miniaturization problem of volume profile of a rectangular patch antenna with variable parameters. Okay. So, the resonant frequency Fr, that is omega by 2 pi of the antenna. Okay, that also gives you its wavelength lambda r, that is given as C by Fr. Okay. The thickness of the antenna substrate d and the effective relative permittivity epsilon r of the antenna substrate. So, the goal is to identify the optimal parameters that will basically minimize the antenna's volume profile. So, the antenna part of the volume created by the patch is equal to S, V equals S times D. So, S is basically the surface area of the antenna and D is basically the substrate thickness. Okay. Now, the above mentioned miniaturization problem for the antenna volume profile is reduced to the nonlinear mathematical programming problem with the objective function represented by the maximum gain of the patch antenna, which is G max, given as a function of surface area S and the resonant wavelength lambda r or frequency Fr, which can be related as Fr equals C by lambda r, right. So, it is basically you have reformulated the miniaturization problem as a nonlinear mathematical programming problem. Okay. And here the constraints are like substrate thickness d and relative permittivity epsilon r, which are can be taken as the given parameters of the fixed parameters. Thus, the mentioned miniaturization problem can be defined as follows. So, you want to find the maximum gain, okay, for S and lambda r, for given S and lambda r, okay, subject to lambda r within this limit, that is lambda r by square root of epsilon m mu m should be greater than 4d, but less than equal to 10d. So, d is basically the thickness of the substrate. So, here the last two inequalities basically define the condition for the composite metamaterial to be non-resonant. Okay. So, it means that the resonance phenomena related to the wave diffraction on the lattice of wires are not taken into account, while the resonance inside the wires are basically taken into account. Okay. So, after analysis we finally obtain the values for W mean and L mean. So, W mean can be written as C divided by 2 F R M, okay, times square root of 2 divided by 1 plus epsilon r, and L mean can be written as S mean divided by W mean. So, once you know W mean, you can find what is S mean. Now, what is S mean here? S mean is basically the minimum required surface area of the patch, and F R M is basically the resonant frequency of the miniaturized antenna, okay, that is basically determined from solving a transcendental equation, right. So, from the previous lecture we got to know the maximum gain equation was Gmax given as eta Dmax, which is equal to 8 k naught square by pi z naught s, and then you have modulus of a at theta equals 0 degree whole square divided by real of a again evaluated at theta equals 0 degree times the eta value, which was 1 over 1 plus j naught s divided by real of a evaluated at theta equals 0 degree times square root of omega mu naught divided by 2 sigma I, right. Now, we know that this equation does not basically take into account the fringe phenomena that is happening on the edge of the rectangular patch of the antenna, and this omission may lead to some more complex near field distribution, right. So, as a result, the S11 spectrum of the antenna with composite substrates can contain additional peaks of interest, okay, for the except as a result the S11 spectrum of the antenna with composite substrates can contain additional peaks of interest except for the peak of the main wave. So, let us give an example. For this purpose you can consider the S11 spectrum of the miniaturized inhomogeneous numerical model in the frequency range of 5 to 20 gigahertz. As you can observe here, the other secondary peaks, okay, they also appear at 9.556, then 11.29 gigahertz, 13.72 gigahertz, 14.45 gigahertz, 15.93, 16.84 and 18.57 gigahertz correspondingly. So, these are all secondary peaks, right. Now, these peaks are of interest with a viewpoint of the possibility of the miniaturized antenna to be reconfigurable one in frequency functionality, right. So, the FDTD simulations for the far field patterns, okay, and efficiency and power gain of the frequency peaks have shown that the peak located at this frequency of 16.84 gigahertz may be of some interest, and you can see that here, okay. So, the blue one basically shows that 16.84 gigahertz and the red dotted one shows 7.38 gigahertz, okay. So, this is basically the far field pattern in H plane, this is the far field pattern in E plane, okay. So, indeed you can see by comparing the far field patterns of this 16.84 gigahertz with the far field pattern of the first peak, okay, that is at 7.38 gigahertz, okay, and you can assume that the miniaturized patch antenna, okay, on this composite or metamaterial substrate can be multi-band and multi-directional, as you can also see here, right. Yeah. So, this is especially evident from this 3D radiation pattern which is shown here. So, here the figure shows you the 3D radiation far field radiation pattern of the miniaturized antenna at the main peak frequency, which is 7.383 gigahertz, the figure on the left, and you can also see it for the other frequency, that is 16.84, which I have considered. So, the key finding here is that the maximum power gain at the frequency of 16.84 gigahertz is also not bad. It is 6.87 dB, which is obtained at an angle of theta equals minus 10 degree, right, and it has got an efficiency value of around 71.73%. So, this result is particularly quite interesting from the point of view of designing reconfigurable compact antenna systems in frequency functionality and polarization. So, taking into account the case of standard numerical model with composite substrate, it is logical to conjecture that the intensity of near field distribution around the miniaturized antenna at frequency of this 16.84 0.84 gigahertz is quite low, isn't it? And figure 1 here basically shows you the near field calculated at a cross section of y equals 0. Figure 2 tells you about near field calculated in the middle cross section along the x axis of the patch antenna. So, there are two cases here considered, A and B. So, A is for the standard homogeneous numerical model calculated at 7.307 gigahertz, and B is basically of the miniaturized one using the metamaterial. Okay. So, that is obtained at 16.84 gigahertz. Okay. So, both the figures basically show you the FDTD simulations of the near field distribution. Okay. And this tells you also about the similar low intensity near field being observed in the standard inhomogeneized model as well. So, what are the implications? So, it basically says much for the above mentioned idea for using additional resonant frequencies of the patch antenna on composite or metamaterial structure. The appropriate FDTD simulations have shown that the same quantitative or qualitative result takes place for the standard inhomogeneous model. Okay. So, this basically enables us to come up with a general conclusion about the multidirectional and multi-band nature of the patch antennas on this kind of composite or metamaterial substrate, right. So, what are the design advantage of this miniaturized design of microwave antennas? They allows integration of receiving and transmitting functionalities in a single antenna system. They also eliminate the need for multiple antennas in communication systems, and some potential application of such a design could be like avoid the use of multiple antennas. For instance, you can use the same antenna operating in the GSM 1800 megahertz band and also for WLAN 2.4 gigahertz application bands. Okay. So, that allows you miniaturization of the overall antenna system. So, with that we conclude our lecture. So, we will start about discussing the far field focusing of microwave antennas with composite and metamaterial substrate in the next lecture. If you have got any query regarding this lecture, you can always drop an email to this email address mentioning the course title and the lecture number on the subject line. Thank you.